When physicists develop a model, they're finding a pattern that explains what they are seeing in their experiments. In the everyday world, we're pretty good at detecting patterns, but some patterns are more complex than others. Here's what I mean. You know those music visualizers that you can find on digital music players? The ones that use information from the song you're playing to alter and transform the animation. The result is a complex animation, but rhythmic and beautiful. Now, imagine that you lived in a world of music visualizers, but you couldn't hear the music. As beautiful as it seemed, it would be difficult to understand why your world looked the way it did. But if you were the curious sort, you could, by careful observation, start to find patterns in what you see. And with some creative thinking, you could even reconstruct the underlying music. And with some clever modeling, you'd discover little things called notes, which combine in different ways to create your world. The particle zoo presented a similar problem. What was the pattern that connected these particles together? Physicists did eventually discover a pattern by arranging groups of particles according to certain characteristics. The pattern revealed that most of these particles weren't fundamental at all. They were made out of a combination of more fundamental particles called quarks. There are 6 quarks in all, 12 if you include their antiparticles. The up and down quarks are particularly important for us because they make up the protons and neutrons that we find in the everyday world. Each proton or neutron is a bundle of 3 quarks. 2 up quarks and a down quark make a proton. 2 downs and an up make a neutron. While quarks seem to solve the problem of the particle zoo, they left physicists with a new one. How do these quarks stick together in the way that they do? The answer required coming up with a new fundamental force of nature called the strong force. The strong force is a fundamental force like the electromagnetic force, but it acts very differently. A quark can have one of 3 charges, which are labeled as the colors red, green, and blue. Combine them together, and you get a color-neutral particle. And while the electromagnetic force gets weaker the farther you get from a charge, the strong force is weaker nearest the particle and actually gets stronger as you move away. Now, think about that for a moment. As long as the quarks are near each other, they're bound together loosely. But the moment they try to separate, they experience a stronger and stronger force that keeps them confined. A bit like an elastic leash that pulls back the further out you pull it. That makes it nearly impossible to separate quarks from one another. What we call a proton or a neutron is really the very, very small area where a group of quarks is confined by the strong force. That nucleus that Rutherford discovered so long ago is actually a seething mass of quarks held together by the strong force in groups of 3s, which we call protons and neutrons. And around those, held more loosely, are the clouds of electrons. But the complete model of particle physics involves more than the atom. It has to include all particles that exist in the universe. The current model of particle physics is called the Standard Model, and it describes all the fundamental particles that we know of and the forces that make them stick together. It's one of the most successful models ever. It can make predictions about particles to an amazing degree of accuracy.
If you take the particles that we know about, and you ask, what's the most general way in which those can interact at low energies, consistent with quantum mechanics and relativity, the Standard Model is it.
I'll describe it briefly so that we cover some of the particles I haven't mentioned so far. First, there are the particles that make up everyday matter: the electron, the neutrino, and the up and down quarks. Then there are what we call the 2nd and 3rd generation of these particles, more massive and unstable, but otherwise identical to their lighter cousins. In the Standard Model, there are also particles associated with each kind of force. These force particles, called bosons, carry the information of a particular force. For instance, the photon carries the information of the electromagnetic force. the gluon for the strong force, and the W and Z particles for another force called the weak force. So these are the particles that make up our universe and that have been detected in particle accelerators so far. Now, it's one thing to make a list of particles, but a complete physics model must describe how all these things relate to one another.